101, and it's my privilege to introduce Dr. Barry Boehm, who's not only our chair of the SERC Research Council, but the principal investigator of the ilities Tradespace and Affordabilities Project, which is a multi-year research task that's coordinated many of our collaborating institutions, but is also our SERC Talks editor-in-chief. Dr. Boehm will be leading our discussion at the end of today's presentation, as well as introducing our esteemed speaker in the talk. So Barry, with that, I turn it over to you.
Okay, good morning or afternoon. Yeah, this is the final talk that has been looking at distributed autonomy and summarizing and taking different perspectives of what the complexities are of having a number of autonomous agents trying to collaborate with each other. And so we had the talk by Azad Madni, who was addressing how are these autonomous agents going to learn about both where their co-agents are, and also learn about where their adversaries are. There are more general things about autonomy that people have been discussing, which we did in the last couple of days in Washington, D.C., and decided to continue having other aspects of autonomy. So the next three talks in the first half of 2020 are going to be on autonomy and trust, and basically saying, if you have all these agents who are trying to maximize their particular participation, but may have vulnerabilities, and so we're going to have three talks on that topic in the first half of 2020. So for now, though, let's go ahead with Ray Madachy, who is going to address both the operational aspects of distributed autonomy, and then also some of the cost impacts and ways to estimate and control the costs. So Ray, you're up.
Okay, thank you very much, Barry. All right, good morning and afternoon, everyone. My name is Ray Madachy. I'm from the Naval Postgraduate School in the Systems Engineering Department. I'll be answering the question today: how can system architecture and cost models be integrated for UAS Unmanned Aerial Systems Tradespace analysis? And we'll see that there are several ways that this can be done. And next, this is a group effort, so let me introduce my collaborators here. First is Dave Jakes from the Air Force Institute of Technology. He, of course, is our domain expert in unmanned aerial systems and also models their architectures with different model-based system engineering tool platforms. So Dave gave the previous SERC talk describing his small UAS reference architecture, and that is used in this research, as you'll see. Also, coincidentally, he's hosting me at AFIT for my sabbatical this fiscal year, so I can learn how to build and fly small UASs and also conduct research in autonomy. That's his big role here. Next, we have Kristen Giamarco. Her contribution here is in formal behavioral modeling, specifically with the Monterrey Phoenix tool, which serves dual purposes in this context. That is for behavioral analysis and cost estimation, both. I'll explain that. And next collaborator, Mike Green from our Department of Naval Postgraduate School. He works on the product line modeling aspect, and it's been applied to naval combat systems, and it's been very successful. So that's just the stage for the UAS domain because of the generic aspects of these combat systems. All right, so if you saw that animation, there's a quick example of some coordinated semi-autonomous agents. All right. So here's the outline I'd like to go over today. Introduction and background. Now, first of all, again, as Barry said, we've had some prior SERC talks here. Azad Mani talked about distributed autonomy. So those are some of the behaviors, like the Markov state decision machine here for some of these architectures that we're modeling. And Dave Jakes most recently gave you the presentation on his reference architecture. Hopefully some of you heard those as well. So here are the main sections we'll go over today. Talk about how we can use SysML and link that to systems engineering cost models. Next, we'll talk about system behavioral modeling. That's the work that Chris and Gianmarco is doing, and how we can link that with software cost. And then those two aspects will be part of this case study here for a remote targeting system, where we'll look at two different architectural variations and try to cost them out. And then next, the system product line architecture, variant modeling, and product line costing with return on investment. Now, to be fair, I really have too many slides here to go over without, missing some important details. So this section here on the product line architecting, just consider this an addendum for now. I don't think we'll have time to adequately go over it, but unless we have a lot of free time at the end or questions lead to it, I'll go into that. But for now, plan not to, just not enough time. And then conclusions and future work. Okay, so there are two different funded research projects here contributing to this. First one is with the SERC System Qualities Ontology, Tradespace, and Affordability Project, SQUOTA. Now, Barry Bain was the lead PI on this, and this is what got us together, AFIT and NPS working together. And this is a multi-year project, 7 phases, and more recently in the NPS Acquisition Research Program, where we look at the product line modeling aspects. So first on SQUOTA, this includes joint research by ourselves and AFIT. We're developing trade-off analysis methods, trade-off with respect to affordability and other performance measures, using architecture and cost models applied to various case studies for unmanned aerial systems. And the ARP research, here we developed product line modeling methods applied to naval combat systems, and those came out very well, and so we think that's going to be easily applied to the UAS domain because of the generic aspects there of these combat systems. So why do we care about this? Well, first of all, let me go back up here. I need to point out here that so on the SQUOTA project, I think collectively there's about 6 theses here done at AFIT and NPS that contribute to this. And the ARP research, there were 3 theses here at NPS and a group capstone that contribute to this. Very important here, the student involvement really helped further the research. And so this addresses the problem here that in DoD, normally you have people doing performance-based modeling and cost modeling, but these are distinct activities usually, normally done by different groups, and it's done in effort and imperfect communication between the product architects and the cost analysts. So that's what we want to improve. And so the focus here is at the interface of these models here, so that ideally we can automatically extract these system size attributes from the architecture models at different levels. If you want to estimate just the software development portion, or the overall system, or a group of systems derived from a baseline product line. And then with this interface between the cost and architecture models, cost can be associated with these architectural variants, so we assess the trade-offs between affordability and other ilities, including performance measures. Things such as percent of target detection, minimization, false positives, etc. All those good things here. But today we're really focusing on the cost results. That's what we'll be displaying. So in order to do this, we need some translations here between these models and these MBSE platforms, so we can map some architectural elements to cost model factors. So by doing this, we improve cost estimation, and we kind of kill 2 birds with 1 stone. These architecture models serve multiple purposes, including estimation. And then this is all consistent across design and estimation processes, as well as being consistent with respect to the normalized inputs that are assumed by the cost models. And so we save time here because if these architecture models provide this cost model inputs, we don't need independent expertise for cost modeling and extra effort expenditure. So the way this works here, we're using different types of methods and tools in model-based system engineering to evaluate, behavior, performance analysis, and costs in the face of changes. Because, uncertainty abounds, there will be changes, and we also want to evaluate different for the architecture. So we develop these architectures in different environments to capture these military scenarios for actual and notional case studies. They're all relevant. And so we've done modeling with SysML and DODAF, orthogonal variability modeling, Monterrey Phoenix, and various types of executable activity models using different tools. Now, I assume for this audience here that you do not need an introduction to SysML, but I will overview some basic cost modeling concepts. So we're using different tools here. The ones we've used in this project are InnoSlate, Core, and Cameo, sometimes called Magic Raw. So with these architecture models, we develop interfaces for components of the architectures so we can evaluate the cost effectiveness, and then we can evaluate in full trade space, including costs in these integrated environments with static and executable models of architectures. Many of the SysML notations, diagrams are static, but some of them can also be executed like activity models in InnoSlate and some of the other tools. So again, today we'll just talk about the sample cost results, but also these things provide performance measures as well. And all these ilities would be considered in the trade space. Okay, a little bit background on the cost modeling. So cost models, they're simple to understand with known equations, and so it's an easy use framework for performing these broader ability analyses, including affordability. So we're going to use parametric cost models that encapsulate cost system relationships, which are simply mathematical algorithms that relate these cost factors here to compute cost, to describe characteristics of the programs. And so we're going to use some parametric models that are public domain so that everybody knows how they work and they're available for usage, and all stakeholders are on the same page here. They understand why the models produce these results. This is why these are called constructive. People understand why they get the estimates they do and help them plan better. And for all these parametric cost models, whether you're looking at software, system, hardware, etc., system size is the largest source of variance in all these cost models, whether that be weight, lines of code, number of requirements, etc. It doesn't matter. All those are interpretations of size, and therefore it's the largest source of cost of variance. It's the most important factor to capture. So that's what we're focusing on here, our size attributes to go into the cost models. So if you said these are simple equations to understand, here's the underlying most general formula here for these constructive cost models, where the effort, the labor cost, is a constant, which is, a calibrated term here, against historical data, times size, all important size, raised to an exponent b. Now, size is a measure of the work product for whatever thing you're trying to estimate for, whatever's being produced. So if you're looking at software cost, size is lines of code. If you're looking at system engineering cost, what do they produce? They define requirements, so you count the number of system requirements, etc. Now, for both systems and software cost, size is raised to an exponent, which is greater than 1, which gives you the diseconomy of scale, which means, we're less productive as the system size increases. So this gives us a nominal effort here for any activity that we're trying to use this constructive model for. And then this is all multiplied times effort multipliers here to describe other project characteristics like the process, the product, complexities, etc. So this is all interpreted here, this basic formula here for these different aspects, system, software, or product line. And once again, this is called constructive because the user understands why the model gives these results, and you understand the job better by going through the cost model and trying to understand where you rate. So here are the three cost models and different variations of these that we use in this research. So first of all, COSYSMO, Constructive Systems Engineering Cost Model, estimates the cost of doing systems engineering. So in order to use this, we had to have a mapping between SysML entities and COSYSMO size attributes. We'll describe those. Kokomo, which is the granddaddy of these constructive cost models, estimates software development cost. So here we're showing how we can use behavioral model entities that map very cleanly into software size. Then we have COPLIMO, constructive product line investment model, which assesses the cost savings and return on investment of a product line and reusing it across multiple systems. We also extended this at the system level to include hardware development and non-labor cost. And so for this, we had to map model variations into the degree of reuse in the product line. Now, in system COPLIMO, so the software COPLIMO size is lines of code or alternative measures that can be converted to lines of code. Now, in system COPLIMO, we use highly aggregate size measures. It is interpreted size as the number of subsystems, like a radar package. Now, of course, we can redefine size at any level of detail as feasible to estimate from the architecture models. Our variability models are only decomposed to the subsystem level. Okay, now let's talk about our mapping between SysML and systems engineering cost model. First of all, here's a black box depiction of COSYSMO, what goes in and what goes out. So first and foremost, a count of the size entities, the number of requirements that need to be defined, likewise the number of interfaces, the number of scenarios, and the number of algorithms to be defined or developed. So these are the four size entities that we want to count that goes into COSYSMO. And then these are also adjusted by complexity. Each of these has a complexity between low, medium, or high. Today, we're showing all of these rated as nominal complexity. The next phase of the research will account for the complexity values, levels. So here are the size drivers. Other factors go into the cost model to describe the application characteristics, like how complex it is, level of service requirements, et cetera, and then other team factors describe those processes. And then out comes the effort for system engineering decomposed by the phase and activity. So here's how COSYSMO works. So let's focus on these size attributes. It's important to understand these definitions here because these are the linchpins between the system architecture and the system engineering cost models. So requirements, simply the number of requirements for the system of interest at whatever level of design. And these might be functional requirements, performance-based, feature, or service-oriented. All of those count. And I have to do a complete count of those. The number of interfaces. These are shared physical or logical boundaries between system components. These could be internal or external interfaces. These are all things that are modeled in SysML, of course. Algorithms, the number of newly defined or significantly altered functions that require unique mathematical algorithms in order to achieve system performance. These might be things like a Kalman filter for guidance navigation or discrimination algorithm for identifying friend or foe. That sort of level of algorithm. And finally, operational scenarios. This is best thought of as threads that a system must satisfy, including nominal and off-nominal threads. All of these threads have to be accounted for, right, because they have to be system engineered, so there's costs associated with them. So all off-nominal threads are to be counted. So here is our grand mapping here between the size attributes that you can model in SysML and how they map to COSYSMO. So here we have requirements, and they're annotated like this in SysML, and they show up on requirements diagrams, package diagrams, etc. So wherever you see one of these in a model, that's a one-to-one mapping into the kind of requirements that goes into the system size for COSYSMO. Next, over here to model interfaces, we have these simple ports that SysML supports. These show up in block diagrams, internal or larger block diagrams, and these could be internal or external ports. So it's just as simple as counting the number of boxes that you have on your SysML diagrams that are interfaces. Straightforward one-to-one mapping there. Same thing that's defined in COSYSMO. And then we have algorithms. They aren't so cleanly mapped, but these can be expressed in parametric diagrams if they include sufficient detail. And these would be counted as algorithms that go into COSYSMO as the size. And lastly, use case diagrams, and these are fairly well known here. Use cases show up as ovals on use case diagrams, and those are easy to count manually or automatically. And those go into COSYSMO, and then these size entities are all added up, summed, to get the total size to be systems engineered. So these pictures here show the traditional use of the notations, but there is flexibility for extensions of the SysML. You could maybe have some other model elements or stereotypes that might apply. So we developed this mapping method here, and this was initially demonstrated in an NPS thesis by Captain Dennis Edwards, who's in the Army, and he's now teaching systems engineering at West Point. That was the first time this method was documented. So now let's apply this to some unmanned aerial system missions. Now here's a set of notional missions for which AFIC developed the detailed use cases, which were then counted and used for effort estimation with COSYSMO. So these are missions of increasing complexity with variations including the number and size of planes to perform these missions. And these operational threads were complete in detail enough so that we can count them to gauge our relative efforts to implement them. So the simplest one here is have a single UAS go out to search and find a target. Next in complexity is have a pair go out and do the same thing. And then we have these variations of find, fix, and finish terrorist leaderships here, employing, again, different classes of UASs here and coordination between them, different levels of autonomy. So now let's do a relative cost comparison of these, which is pretty easy to do. But to do that, we need to count these mission threads here. Here's the simplest single UAS mission here. We have a launch, think of it as a use case, navigation flight, search and target ID, target tracking, return and recovery. So these could be expressed on a use case diagram, and we conveniently count 5 ovals. It goes into the cost model. So for each of these missions they showed previously, there's use case description for each of these with the flow of events, etc. So when we can count and enumerate these use cases, this is a primary size input for COSYSMO, and everybody is familiar with use cases. So when we do this, count these number of use case threads through these different architectural descriptions here. Here's the relative size and cost comparisons. Now recall that these methods are meant to be applied early in the life cycle when trades are being made. Now, at this point in the life cycle, you don't need an absolute budget at this stage, so relative cost comparisons are valid and useful for making decisions. Thus, a simple count of the use cases here affords this comparison. We don't need absolute estimates yet to choose between. So this is a nominal estimate without accounting for the varying complexities of use cases, and then they would carry additional weights. So we could manually ascertain complexities, but where we want to take this research is to automate the process and assign complexities to these different use cases. So there's a very quick example on how we can use some constructs in SysML to do a relative comparison between different architectural variations. But we'll show a more detailed comparison here for a remote targeting system. Next, let's look at the aspect here for software cost modeling with architectural models. Now, we could do this in several types of architectural modeling. Monterrey Phoenix is very handy and can do it, so we'll show an example with Monterrey Phoenix. So this is a formal approach to specifying software and larger systems here based on behavioral models. And so we have a view of the architecture model, which is a high-level description of the possible behaviors, all the possible behaviors of the system, and interactions between the subsystems, environments, etc. And so with this, you know, unforeseen emergent behaviors can be identified as well. That is one of the big advantages of using something like Monterrey Phoenix behavioral modeling. In this case, we're also going to double dip and use it for costing as well. So in Monterrey Phoenix, the emphasis on specifying the interaction between the system and its environment. So it employs architectural modeling, so we can use this to inform our technical and investment decisions. So we can have atomic and composite behaviors here, and this supports architectural reuse of these behavioral models. And these are executable, so we can help test our system architecture and see, are there some unforeseen emergent behaviors, et cetera, that we need to plan for. So here's two websites here. Get more information on Monterrey Phoenix here, and actually run some models at this website here at firebird.nps.edu, and you're all encouraged to do so. So we said we're going to link Monterrey Phoenix behavioral models with software cost, and here is a model we'll use called Kokomo 2, and here's what goes in and what goes out of the model. First and foremost, a product size estimate, and traditionally we know this is lines of code, but alternate measures can be used such as function points or other measures that may be converted to lines of code. Or the model can be calibrated directly to function points or some other size measure. Then we also have other characteristics that describe the product characteristics like reliability, complexity, personnel experience, process and maturity level, etc. Are we doing reuse? How many years of maintenance to estimate for? How many builds or increments, etc. So these are the inputs at Kokomo 2, and what comes out are cost and schedule estimates decomposed by development and maintenance phase and activity and increment. So let's do this now. How can we use Monterrey Phoenix models here to get the software cost of the system? Well, they model software systems and the user behaviors. And so from this, we will elicit software size attributes. And what we're not showing today, it also allows some of the system size attributes, such as interfaces, can be easily modeled in Monterrey Phoenix. Not requirements as well as system L, but some of the other attributes. We'll just talk about software attributes today. So we extract what's called unadjusted function points from these Monterrey Phoenix models to use in cost estimation. These function points are what goes into the Kokomo 2 model to determine the software cost. This allows us to assess the design decisions and their cost impacts at the same time here. So this methodology was pioneered on a PhD thesis at NPS by Monica Ferris-Stapleton, and she applied it to three well-known function point counting examples that are published by IFPUG, which is the International Function Point Users Group, and we got pretty much a perfect one-to-one mapping here in terms of the expected function point counts and a model of these software systems done in Monterrey Phoenix, a model of the software and its interactions with the user. So a little bit background on function points. So these are synthetic measures of software size, and they're easier to estimate early in the life cycle compared to lines of code. So that's why we're focusing on them. A good requirements or high-level design document would be adequate to get the number of function points to be developed. They've been around a long time and are well-defined counting standards. So consider an application here, some software application, draw a boundary around it. Essentially what you're doing here is counting what goes into the software system, the inputs, the outputs that go back to the user, inquiries that go back and forth, external interface files with other systems, and external inquiries. So it could be other external systems here that the system is talking to. So we're basically counting these things here, the number of external inputs, data that goes into a system. For example, if you have a web page, just count the number of data fields and the complexity of those data fields. external outputs, the things that you see on the screen that the system provides back. We count those and their complexities. Internal logical files used, or databases, and external interface files. The way this works is you count all these things here, and you roll these up to get an overall unadjusted function point count here. There's some other adjustment factors and get a final count. And this final function point count goes into a cost model. And it's very handy here that the Monterrey Phoenix has an abstraction of these things that are the same as function point entities. So we aren't going to go into what the syntax of all this means here. On the right here is a portion of one of these test cases here where we can count function points. And on the left here are these notations here on what we're counting and how they are coordinated with function points. This here is just a little mini picture here of the execution trace of this model here that shows the interaction between the software system and the users. But the point of this slide here is to show how we can extract function point counts here based on these syntactical constructs here in the Monterrey Phoenix language, mapped to function point entities. So to make a long story short, this page here shows that there are 3 function points shown on this page. And so this is a portion of a model. So we have tools that we created here that can parse these Monterrey Phoenix models and extract these automatically. They can be done manually as well. Now, here's a resulting estimate here from a Monterrey Phoenix model here, from these test cases here. And the total was 88 function points. You put that into the Kokomo model here, and here's the final result here. 16 person months of effort, 9 months of time, this much cost here at a certain rate here of $20,000 per person month. And so this shows here they can get a cost estimate here to develop this application here from its behavioral model in Monterrey Phoenix. So this is not a UAS application, but it shows that it can be applied here. But next we will show this in an application here for unmanned aerial systems. Just checking that there are no questions yet. I don't see any, okay. So let's look at this case study here. I will now include these concepts here of mapping to systems engineering and software development cost models, the remote targeting system. This is actually our second iteration through this case study for several reasons. First, we modeled this in core, this remote targeting system. Now we've put in a new platform, Cameo. We're also reassessing the software costs with new methods. First, we just look at the systems engineering costs. Now with Monterrey Phoenix, we're going to add more detail there for the software cost aspects. So in this case study here, we have 2 variants of a remote targeting system that we're going to compare the costs for. We're also comparing the performance measures to other simulation models, but we're not showing those results here, just the cost results. So here's some of these details here on these 2 architectural variants here, with and without autonomous target recognition. Don't need to go through all these details. And so both these variants are modeled in SysML, from which the cost estimates are directly derived. We also have executable models of the remote targeting system that we're not showing you today. So in the final tally, you would put all the results here from the cost and the performance measures here in your trade-off decisions. Okay, so these are the use cases here for remote targeting system. These are related to the composite behaviors here for autonomous systems agents that Dave Jakes talked about a couple of months ago. Here we can clearly see 7 use cases here for these remote targeting system. Perform setup, launch and ingress, perform search, perform surveillance, and we'll blow this one up later, plan mission, self-destruct, egress, and recover. So these are the 7 use cases here that are fully modeled in this Cameo model. And again, easy to count 7 use cases, and we're not addressing the complexities of these at this time. Now the question comes up, how much detail should be in the use case consistent with the cost model assumptions? So here's a golden example to try to answer that question here. And so the question is how much detail, just enough requirements, complete and consistent to set the stage for implementation. We believe this is what this example shows. It must include all the alternate flows and other interruptions here to the primary flow, because all of these have to be designed for and implemented. Systems engineered and finally implemented. So from this use case level, we don't need to go through all these steps here. We know how a use case is structured here, but this is the amount of detail, just the end of requirements and the beginning of high-level design. So from this, it can be implemented. An activity model can also be created from this, or other simulations can be constructed. In the core platform, for example, it can take this use case and develop a first cut activity model. Now, what we're going to do is take this, and it was sufficient to create a Monterrey Phoenix model. So Kristen Gianmarco took that use case here. Nothing more was needed here, and she quickly developed a Monterrey Phoenix model. So here's just a top view of the model here. There's more equations in there. Here's one of the traces here, an execution trace for the primary flow. And you can see these are like swim lanes, sort of. This is an operator described in the use case, ground station, air vehicle, and off-board communication. And here are some of the events that happen. And they're ordering per the use case primary flow. Now this model here in Monterrey Phoenix actually gives you 16 different possible event traces here. Here's just one of the 16. So by evaluating these 16 traces, you can look at, emergent behavior as well as estimate the software development cost. All of these different possible behavioral outcomes need to be designed for, right? Now, what we want to do here is extract the software development cost, right? We haven't quite got to this point here. This is a brand new model here. And in our previous tool that we had where we extracted size entities from Monterrey Phoenix, we assumed that the data items being processed were relatively mundane, like flat files and simple databases. But in this case here, for this unmanned aerial system, these are real-time communication message flows here that complicates things, and we need to account for that in the function point extraction, and we will be doing that. Here's just another example trace here if a new mission plan was uploaded in the mission during the primary flow. Again, this is a second of 16 different possible traces that Monterrey Phoenix can provide, or provided here with that simple model. Now here's some of the requirements here for the remote target system. This is the last legacy chart from core. Again, we've converted this all to Cameo. And of course, this is a subset of requirements that look similar in Cameo anyway. So this is a one-to-one mapping. Here's one requirement, command destruct. Here's another one, another one. Here we see 5 or 4 requirements here that would be counted as inputs to COSYSMO. Here's a portion, some block diagrams here showing some interfaces, which again are just these ports here, internal and external ports in these block diagrams. So one can manually count these blocks, ports, or create some tools, and we did that as well, like with InnoSlate. So these represent linkages, and so we count these boxes to enumerate interfaces here for the cost model. So here is our baseline estimate here for the remote targeting system here. We didn't show you all the SysML entities, But here's a total, not counting for the complexities. In this model here, in Cameo and Core, for the baseline RTS, 31 requirements to do, 25 interfaces. You didn't model algorithms per se yet, and 7 operational scenarios. Remember, we counted the number of 7 use cases. And given this, here's the nominal estimate, point estimate. And next, we'll take this into a Monte Carlo analysis and extrapolate full program cost. I'll point out again here that all of these things were rated as nominal, but we know that not all the requirements are created equal. So next pass, we'll tag complexity levels to these entities. So here's a baseline estimate for system engineering. Remember, now we want to compare 2 different versions and also look at full program cost. So this is a method here where we have an extrapolation from the Cosysmo estimate to get full program cost, assuming a fixed percentage. And here's the full distribution here from roughly 18 million all the way up to a little over 50 million here. Distribution cost here for one of these variants of the architecture, the remote targeting system. By the way here, when we get a more detailed software cost from Monterrey Phoenix, it will replace the fixed portion of software cost assumed in this approach here, which is a simple extrapolation from system engineering to full program cost. And finally, this is all about comparing the cost of different architectural variations, while comparing performance measures as well, which I'm not showing here. But for the system engineering cost, with the automatic target recognition, yes, it appears to be more costly than the baseline without it, but there is a little bit of overlap here in terms of the distribution here of the cost. Roughly about $1 million for system engineering cost here, and the extrapolated full program cost between the 2 variants we see here between 20 and 40, and a lot of overlap here in terms of the distribution of the full program cost. So these cost comparisons that would be considered in the trade space in conjunction with other technical performance measures that other simulations would afford, such as executable activity models. This is just showing the cost results. So here's a section which unfortunately we don't have enough time to go over in adequate detail here. If some of you have questions later on, I'd be happy to answer these, and we'll just have to leave this here for your own study. Maybe we'll talk about this in another venue on how we do product line architecture variant modeling. So again, this was applied on naval combat systems here. We got very good results. In fact, we were able to compare some of these here against empirical data here for the Aegis ship, and it very much matched empirical data here in terms of software cost and cost savings. Here's a preview of the kind of thing that the product line model shows you here. For a cruise missile product line here, if you develop 7 instances, you get a large return on investment by reusing the product line baseline. Again, so I don't have adequate time to go over all of this, but this will be taken into the unmanned aerial systems domain. Okay, so let's look at the conclusions and future work. So first of all, we found that cost models do provide a simple framework for forming these broader ilities and affordability analyses when tied to product-oriented architecture models, such as SysML or Monterrey Phoenix or other types of models, like the product line orthogonal variability models. So by developing these mapping rules here between these model-based system engineering platforms and the cost models, we showed integrated approaches for architectural analysis, behavior, performance analysis, and cost estimation applied to real DoD mission types. So we found a strong correspondence between the SysML constructs and system size measurements, system size measures of requirements, very clean mapping there, interfaces, one-to-one, algorithms we need a little better definitions here in terms of the level of details needed in the algorithms. In operational scenarios, is a pretty clean mapping there. But again, we do want to look at additional attributes for modeling the complexity levels of these size drivers. And there's various ways we can do that. I'll talk about that in the future work on the next slide. Look at a number of associations, dependencies, etc. We also found that Monterrey Phoenix language encapsulates function point measures for software size as well as some of the system size attributes. So there's an overlap there in terms of SysML that can also elicit some of these system size attributes like interfaces and scenarios. We found when we did the naval combat system modeling here that these architecture variabilities for software and hardware can be quantified with orthogonal variability modeling and used for costing and investment analysis. So I should mention a little bit here that the successful results in naval and combat systems gives us high confidence and can be applied to unmanned aerial systems. For example, here we were able to compare model results here with actual data on the Aegis ship here, and it matched very well in terms of product line size, cost, and cost savings. Since combat systems are kind of generically similar across domains here, they take sensor inputs, analyze the sensor information, and act upon it. We think there's a good possibility that unmanned aerial systems can be modeled similarly. So a lot of future work here. Continue expanding the Cosysmo framework for architectural trade-offs with better fidelity for hardware aspects. And we're going to be doing this with AFIT, applied to the small UAS domain. We did this a little bit on CubeSats and realized that yes, hardware weight and things like hardware descriptors aren't captured in Cosysmo. We need to do better than that for hardware aspects. Did not give us the actual results that we expect here in terms of hardware cost. I see there's a question or something here. Let me see if I can address this. Oh, have you automated? Yeah, Yi. Hey, Yi. Have you automated the Monterrey Phoenix calculation function point inputs? Yes, we did. And as I said, Yi, we did that with an underlying assumption that the data items being used were relatively simple. So we need to redo that for the higher complexity of these real-time messages being passed. So yes, we did automate that. Requirements count. Is that only functional requirements? No, we have more requirements, all those including service-oriented, feature-oriented performance, not just functional. So those are two questions I see. Hopefully that answered those. All right.
Thank you. Thank you, Rick.
Okay, sure. So I didn't see those before. So here we also want to model the complexity levels of size attributes. For example, to assess the complexity requirement, to assess requirement complexity, we could enumerate the number of associations and dependencies to other model elements, such as dependencies to other requirements. This might be similar to like measuring fan-in and fan-out measures seen on a hierarchy. So these could be automatically measured, and these would be consistent with the complexity definitions here used in Cosysmo. Use cases can also be similarly quantified for complexity levels. Now next here, so this is really hot here. You know, Dave Jakes is working on this small UAS reference architecture, and this is just a perfect fit here for product line modeling. It is a product line baseline is what he did here. And what's really nice here is we now have an implementation of this for the wide area search and surveillance software agent. This is one of the slides that Dave Jakes showed you a couple months ago here for this software agent here for the wide area search and surveillance. Now, I was back there at AFIT in November here and met the graduate students that have developed this, and now we have their baseline here. So this is written in Python, and it's very conformant here to these blocks here you see on this diagram, this block diagram, almost a one-to-one mapping here. So this is everything they needed here to develop this software agent implementation. So now we're going to be measuring the software size and other characteristics and tie this to the product line model. So this is really hot. Really looking forward to this. This is brand new, late breaking. So this is perfect for a product line analysis. Next, we also want to enhance the product line cost models for individual component complexities and non-homogeneous change percentages. The default COPLIMO assumes that these are homogeneous, but they are not in the real world. That's one thing we found out here on the Acquisition Research Program research. Develop guidelines for practitioners on modeling decomposition levels of details. And so there are all sorts of good questions here on what level of decomposition should we go to. So we would like to document that better, as well as talk with some of the vendors here to maybe get some of these things working in their tools. Collect more empirical data here for further calibration and validation of the cost models. And here's something that we can do here. Data mining of models here for new correlative measures to size and or cost. So this would require access to models from actual programs, and maybe even extract some new meaningful entities. For example, function points were initially defined decades ago, okay? Cosystemol inputs were defined before some of these model-based simulation tools were prevalent. There could be other model entities, indicative of job size, cost models. So with enough data, we could apply some machine learning approaches here and find out what is these other things being extracted. Maybe we don't need function points, or maybe there's something better that we use to correlate to size and cost in these models. So maybe we can apply data mining here to this. All these would be valid here for theses, et cetera, here at NPS or AFIT. So that's what I have. Here's some of the references here, and I guess it gives us time for a couple of questions maybe, if there are any.
Perfect. Thanks so much, Ray. Yeah, I believe, Macaulay, you're unmuted, so you can ask your question directly if you'd like.
No, I'm fine. He has addressed the question. I wanted to find out about the requirement count. He said it's all the requirements. I wanted to make sure if he was only counting functional and maybe performance type of requirements, but it appears he's counting all the requirements, probably including the business of requirements.
Exactly. Right here. All functional, performance, feature, or service, or other types that we haven't even specified here. All of the above, and that is the answer there. Yes, good question.
Great, thanks, Macaulay. And we had another question from Matthew House, which was, how were the OVM diagrams created and integrated with the model? What was the tool and execution that were used?
I'm sorry, I forget which tool we used on that. That's a good question as well. Yes, I'm sorry I can't answer that right now. I wish Mike Green was on the phone and he could answer that quickly. I don't know, does this look familiar to anybody, this tool? God, which one was it? Good question. So here's a view of the orthogonal variability model. I'm sorry, I will find out which tool that we used for that. Again, I don't recall.
No problem. We'll include it in the file.
So, yeah, student did this. I don't recall.
Gotcha. You mentioned the capstone was a contributing part of this. How did that break down between the research tasks and projects?
So this is a group capstone where they did a cross-domain product line analysis here for the acquisition research program.
Hi, Ray. This is Yi.
Oh, hi, Yi. How are you?
I'm good, thank you. I have a question. I know you talked about some examples regarding the models in Monterrey Phoenix.
Uh-huh.
So I'm wondering if you have some teaching materials that you can share. This will basically for demonstrating the modeling simulation part to kind of undergraduate software engineering course.
Yeah, one second. Let me get the slide here. Basically, those URLs that I showed you would be the best starting points. One more time here. Yeah, right here, Yi. This is the best starting point here. Go to this wiki here.
Okay.
And if you really want to get started modeling right away, go here. And there are some available models that you can just import and start running right away. And if you have any other questions, let me know, and I'll give you some files, and you'll see it works right out of the box. pretty nice.
I see. Do you see it's like appropriate for graduate level, or you can try to adapt it for, and I'm sorry, only for master level, or it's okay, or it can be adapted for undergraduate? In your
I don't see why. I think undergraduates could use it as well. I would encourage that.
Okay, I'll follow up with you offline.
Okay. Now again, it's a formal approach.
Mm-hmm.
So if they're in that mindset, okay.
Yes. Yes. Thank you.
Sure. Are there any other questions?
For anyone did, let me just double check the email. If anything, it's just praise for the talk. More comments than, oh, looks like Antonio has a question. How does the system value or system size evaluated in Kokomo take into consideration hierarchical representation of the system in SysMal?
Yes. I think you're alluding to what level of decomposition. So basically, you decompose to what we call the C level, and that hierarchy means it's just the end of requirements ready for implementation. Sort of like how I described the use cases at what level they should be decomposed down to. So I hope that answers the question. We can give you some other materials on Kokomo on examples of what we mean by C level. C, we mean SEA level. Not above the water, not below the water. Is that what you're asking? Does that help?
Can I just have one more question?
Okay.
Yeah, so I was wondering, like, what was your experience in terms of, handling the cost of integrating COTS?
Oh, COTS, yeah. You know, we didn't have to address that yet in any of our case studies. However, we will be doing that for unmanned aerial systems here because a lot of these things are, well, they're not commercial off the shelf, but open source that will model similarly. Actually, we did assume that these have to be developed from scratch here. We need to address that in terms of open source and off the shelf. So very good question.
Okay.
Yeah.
Sorry, I'm gonna look forward to some of your work on that.
Very good. All right.
I have a follow-up on my previous question.
Yes, Antonio, go ahead.
Yeah, my question was more like, given the 4 inputs that go from SysML to Kokomo, the requirements interfaces, the algorithms, and the scenario.
Okay.
How does that take into account, as you said, the composition level? If we have 2 architectures that are with the same requirements, interfaces, and scenarios and algorithms, but have different overhead in terms of like how they're developed and the number of levels, I would assume that they would have a different cost of development. So that the system size should be different, but I don't see that into the model. Like, do you guys take that into account? Do you think it should be taken into account or not? That was the question, I guess.
So Kokomo is for submitting a single system. You're talking about maybe a hierarchy or maybe a system of systems, maybe?
No, just the hierarchy
Okay.
of the system. As you decompose your system, the system itself, if you have 2 different architectures and one with a high level of decomposition and one really flat, I would assume that would give you a difference on the development cost. So if that's what the system size will be over there, but I don't see, like, I would put it into that system size somehow, doing SysML, I guess, I don't know, reference properties, just to make sure that you have hierarchy. But I don't know, like, if you guys have thought about that and if there's a reason for which you didn't do it. Like, I'm just, considering that if I want to know, should that be taken into account or not?
Well, maybe we can continue this offline. I'm not quite sure what you're asking. Maybe we need to see.
Yeah, definitely.
Okay.
I can send you an email.
Okay, I'm sorry about that.
No.
Okay.
Thank you.
Yeah.
Thank you for the talk.
Again, as long as they're all normalized, the same level of decomposition, but maybe that's not what you're asking exactly. Okay. Happy to address that.
Yeah, Ray, are you able to factor in some of the things that Zadmodny is going to be adding to in terms of the coordination and learning kind of aspects?
Yeah,
how those would be a size aspect, but there might be other complexity kinds of things.
Yes. So Barry, I think what you're talking about is some of these would go into this type of entity here, the markup state machine, these decision rules. Yes, absolutely. So these are the things that are, again, being programmed or implemented already for wide area system surveillance. And here's where we would plug in some of the Zadmodny type of algorithms is right here. Yes.
Oh, good. Yeah, great.
There you go. Markup state machine. Yeah, just what we want to do, right?
Ray, this is Macaulay again. A very quick question to follow up on the requirements.
Yes.
So the requirements, at what level before you count those requirements? Because you said the CSML, right? So have you, decomposed them to the point that you have atomic requirements, or this is very early in the game when
requirements? Yes, we would. Yes, the answer is yes. You want those to be atomic requirements,
okay.
Right? That low. Yes.
Atomic requirements, but only at the maybe a spec level, not to subsystems yet, or is it at the subsystem level?
So, it could be at the system level if I'm following you. Yes, it could be.
Okay. Because I'm asking, right, when you're trying to get a cost, right, you probably want to get a cost. This is probably at pursuit of
requirements.
Proposal time, right? So at times you don't have requirements are still a bit fuzzy. So that's why I was asking that question. Okay. Thank you.
Oh, you're welcome.
Ray, I'm not sure if I'm unmuted here. I'm unfamiliar with Zoom. This is Rama Garris.
Oh, hi, Rama. How are you?
Hi, good. I just have one thing about the COSISMO slide.
Okay.
And maybe I'm just missing something fundamental here, but it seems to me if you're trying to compare two architectures and use COSISMO for both, wouldn't they have the same requirements and do the same scenarios and need the same algorithms? So what makes the cost different?
Yeah, okay, so let me show you this case study, like the remote targeting system, basically. So here we modeled, for example, here's some differences here. They wouldn't be the same because this one, the ATR variant has some additional requirements on it. So they're almost the same except for these aspects here.
Okay, so it's not really, it's not that you're trying to say, I'm architecting a system, what are two different alternative ways of constructing the same system? That's not the problem that you're solving.
We're looking at two different variations of the architecture, yes.
But so two different, meaning they actually have different functionality?
Slightly different, yes, that's true, yes.
So like this isn't for like an analysis of alternatives where you have two identical things that you're trying to accomplish.
That's correct. That'd be a different case. Correct.
Okay, and in that case, it seems like COSISMO can't really distinguish between those two cases.
Yeah,
right?
I guess not. I guess they would not. Right. If
okay.
Same requirements, correct.
Okay.
Right.
Yes. Thank you for that clarification.
Yeah. Good question. Right.
Thank you so much, Ray, for sticking around after time to answer all the questions. I know that there was a couple follow-ups that we'll post along with the video of today's talk. But thank you again. And just a heads up to all of our attendees that in 2020, we'll be exploring autonomy and trust. Barry, did you have any other items that you wanted to mention before we sign off?
No, I think that's something that we're still lining up the speakers for. So we'll follow up and let you know as we get more detail for. But yeah, basically it will be the first Wednesday in February 2020.
With that, thank you everyone for joining and happy holidays. We'll see you in February of 2020, if not before.
Okay, thanks everybody. Thanks, Ray.
All right, thank you everybody.
Yes, Ray.